The girl, he cannot make it. Oh, those two. Are they coming? Yeah, I thought I want to discuss assignment first. One. Hang Wei not here. Is Hang Wei coming? Yes, sir. Is he on the way? Okay. If you guys look at the assignment feedback already, and I also posted the solution, so you can compare, okay? And then see where you lose mark. If you think that you can get more marks, then you can kind of talk to me, okay, afterwards. Yeah. Is he coming? Sleeping, ah? I have to see later. After I discuss, and then yeah. I see. Oh, coming. In that case, maybe we discuss first then. So this time we have. Oh, come here. Okay. Yeah, I wanted to discuss assignment first. So good that everyone here first. So for this assignment, right? So if you are 20 and below or around 20, so you will be in a dangerous zone. Okay, so please work harder. Okay, if you are around 20. Okay. And we got about two high score, 47, 48. One of them is Larry, the other one is Jack, Chen Jack. Okay. Yeah. So maybe can get help from them if you need. future. And maybe it's the first time you do my assignment. So for my assignment, right, I require to write, to explain everything, okay, but not to write long essay, but enough details, okay, and then every equation need to be followed by a reasoning, okay, yeah, need to explain every line. Okay, so if you see my solution, I also explain every line, okay, and okay, so let's discuss assignment first. Okay, I think first question is pretty straightforward for you. I think a lot of you managed to show it, but you didn't mention what you use. Okay, so usually I take off marks here if you don't mention, but I'll only take off 1 mark. Okay, yeah. So if you're gonna split your sequence, okay, split your limits into your sequence. Why do you do that? Because of convergent uh, sequence. Okay, property of convergent sequence. So limit act like a linear operator. Okay, okay. So you need to write why you can split the sum. Okay, you can bring limit into the summation. Okay, you need to write it. And then number two. Okay, uh, how do you feel about number two? Do you feel like I never touched this before, or I somehow touched it but I didn't go big into it? What do you feel when you read question two? That's a kind of loss, or loss. Okay. Vincent, what do you feel when you read first time reading question two? Hmm. You want to discuss? No, no, no. I mean, when you first time read this question, what do you feel? When you first time getting this question, you don't understand. Okay, maybe ask someone else. Lo, how do you feel when you get this question? Easy. 奇怪，weird，没有学过，没有学过。Okay, yeah. We don't learn this definition. Okay, but okay, what is AN here? AN is a sequence. We learned that what is sequence is bounded above. Okay, but I didn't tell you what is not bounded above. Okay, but what is not bounded above? Negation of bounded above. So you need to go and negate the definition of bounded above. Okay, so if you negate the bounded above definition, what you get is for all m there is an m such that am greater than m. Okay, so if you remember, can anyone recall what's the bounded above means again? So what does it mean by bounded above? Huh? So a sequence is bounded above. What does it mean? There exists an m, okay, such that for every small n in n, an is less than equals to m. Okay, so you take the negation of this one. Okay, so negation of the existential become a universal. Okay, and then for all become there exists, and then the inequality is solved. Okay, so the first thing you need to do is you need to be able to do the negation. Okay, and then from this negation here, you need to prove that this statement is true. Okay, so given all m, okay, you need to find a little m such that am is greater than m. And I think more straightforward for you is you use the log stuff, right? Okay, yeah, it's okay. But here is the analysis trick here. Okay, so because I assume a greater than 1, okay, I can write a as 1 plus some number b. Okay, so the good thing about this procedure is if you expand a to the power n, okay, you will always have one sticking outside. Okay, so how to make this whole series? Okay, I think there's a typo here. I need to fix it. Okay, so how to show that this whole series is greater than some m? Okay, how to show? I just need to make one of the term greater than m. That's all. Okay, because all of them are just addition of positive number. Okay, and there's a plus one already. Okay, so let's say if I can make nb, okay, is greater than m, surely, so if nb is greater or equal to m, surely 1 plus nb is strictly greater than m. Okay, yeah, okay, hello. Okay, hello. This is a kind of classic analysis trick that you need to pick up. Okay, so how we choose this 1 plus b really depend on my condition here. Okay, my condition here is a greater than 1. Okay, so if a greater than 2, then maybe you can write 2 plus something else. Okay, so the description of a is because of my assumption. Yeah. Yeah, I think it's a usual thing you experience. You don't know how to do my assignment. Okay, because when I pick this question, right? This question mostly won't be standard. What do I mean by standard? They won't come from standard textbook examples. Okay. So why I pick like this? Because I really want you to understand the concept and then use the concept. Okay. I don't want you to just copy paste. Okay. Not just copy the solution, change some number and then compute. Okay. I want you to understand what the solution is doing. And then in future, you should be able to write down your solution. Okay. Does it make sense? Does it make sense or not? Okay. Yeah. I think this will be a constant feeling about these assignment throughout this semester. Okay. I hope you can get used to it. Is it okay? So whenever you see the question, right, straight away go back to definition. Okay. Like here appear bounded above. So you need to go back to definition. What is bounded above? Okay. And then not bounded above, meaning negation of bounded above. And then you need to write down negation. Okay. And then get the statement that you want to prove, and then try and start working out how to prove it. Okay. So first thing you see the question is you need to identify the goal first. And then you come up with a strategy. Okay. So goal is very important. Okay. First understand the question first. Only go and solve. Don't straight away see the question and then search for a solution. Okay. Maybe you don't know what's the solution doing, you know. Okay. So understand what's the question asking first. And then look for a solution. Okay. Okay, part C, number 3. I think most of you done it Okay. And you guys use these ln e to the ln of this, something like this. Is it? Yeah, I think so. Okay. Because in the class I show the limit of 1 plus 1 over n to the power n, right? Using similar technique. So some of you use this kind of method to solve it, but it's fine. Yeah. But for this question, the easiest way is to use squeeze theorem. Okay, squeeze theorem. You can squeeze below by 1 a1n and then squeeze above by k times a1n. Okay. This a1 is special here. A1 is the number that bound everything else. Okay. Okay. And then this hint here is for the k here. Okay. Luckily, not many of you drop into the trap. Trap meaning the hint say that n root of x, but the x here is fixed. Okay. So you cannot consider this x as a sequence. For example, you cannot put n root of a to the n inside, where the x is changing with n. Cannot. Here, x is fixed. Okay. So only fixed x works. Okay. So for example, it will works if you put n root of k. Okay. And then k is some real number. It works. Okay. But you cannot put something like limit of n to infinity n root of okay. So you cannot put n root of, for example, 2 to the power n. Okay, this is not equal to 1, maybe. So you need to put something fixed here. Okay. So this x here means some fixed number. Can you differentiate between fixed number and some running number? You understand? What do I mean by fixed number? Yes or no? Yes or no? Do you know? You don't know? Okay, so if you don't know, make sure you ask, okay? So what do I mean by fixed number? Fixed number means some constant, okay? So for example here, maybe k still a bit. So maybe I put n root of 2, then this one, okay? Or n root of 1000 also works, okay? But you cannot put some sequence here, okay? You cannot put something that's changing with n. Does it make sense or not? Anyway, what kind of x I can put inside the n root when I take limit? For the hint. What kind of x can go into this limit here? Hmm. You don't know? X greater than 0. X have to be greater than 0. And then x is a fixed number. Okay, it's a constant. Okay, it's a constant greater than 0. Okay, can understand? No? Okay, what is the mistake that people do is they put like a1 to the n inside here, and then say that this is equal to 1. This is not true, not always true. Okay. You know why? Change why? Why? Because this number here is changing with n. Okay. So you need to put a fixed value x. Okay. Okay. I think 4 is fine, but a lot of problem is so this question is about sequence, right? So I saw some of you using ratio test, comparison test. Why? You see S and then think that this is a series, is it? So you need to differentiate between the convergence of sequence and convergence of series. Okay, so this is still a sequence. Okay, this is sequence, not series. Okay, those tests, those tests are word for series. Series, convergence of series. Okay, here is convergence of sequence. Okay, so this question here use monotonic convergence theorem to prove. Okay. Next question here. So this question says that a Chinese philosopher called Zhuangzi says that if you take actually a stick, but I put a ruler here. Actually, it's a stick. If you take a stick of length 1 and halve it every day, it remains inexhaustible for eternity. So what does it mean? So it means that you can keep halving it forever. Again, never stop. So please explain this process mathematically and discuss its plausibility in our physical world. So there are two parts to this question here. Two parts of this question, okay? I'm not sure. Some of you didn't answer the second part. Why? You just lose mark. Most of you, if you answered it, I will give you full mark. Yeah, no matter correct or wrong. Because this is an open question. Okay. So if you don't answer, then you lose mark. Okay. So what's this? Most of you wrote down geometric sequence. Okay, you observe that there's some geometric sequence coming in. It's like one time half, one time half time half, one time half time half time half. Again, you say that this converge. This converge. Okay, some of you the argument says that this limit to 0, but you never touch the 0. Okay, this is your argument. Okay, limit of 1 over 2 to the n, right? Okay, yeah. But a more accurate description to this question should be geometric series. Okay, because you have a one stick and then you take it away half, take it away half, take it away half. So it's like 1 minus half, minus 1/4, minus 1/8, minus 1/16. And then actually this is the geometric series of 1 over 2 to the power n. Okay. Yeah. And then let's see what I wrote here. Is it possible or not? Okay. Can everyone see the thing? So is it possible or not? So what did I wrote? So I say one can take a knife or scissors to cut the ruler. So you can use sharp object to cut it. Did you see what? Did you see videos or not? Or short videos? People cutting meat, cutting. They use very sharp object to cut it, right? For example, you need to cut a bone, okay, bone of maybe an animal, okay, like so non-Muslim here, right? So for example, pork bone, very big, or beef bone is also big, okay. So you need that sharp object to cut it. So depending on the material of the ruler, one might need a sharper tool to pierce the ruler. So this amounts to the force per area of pressure applied to the object in order to break the bond within it. So have you seen the YouTube video like they put a compressor to compress everything, see the things can break or not, and then yeah, and then they put a stack of paper go into the compressor and then press it down, and then the paper break. Okay. So for a big object, you can do that. Okay. But for small object, how? Okay. So if you keep breaking down the paper, okay, an object, so you will keep halving it into the atomic scale. Okay. Then, so how to break atom? So how to break atom? So you need a lot of energy, okay, to break the atom into subatomic particles. I think one or two of you wrote about this. Break into subatomic particles. Who wrote this? Who wrote subatomic particle in their solution? Hello. Who wrote? Larry? Yeah, Larry. I think there's one more. Huh? There's one more. Never mind, I got screenshot. Uh, okay, maybe they don't use the word subatomic particle. Okay, never mind. Later we come back to this. Okay, so subatomic particle. So why we need energy to break this? Okay, this is because of the Einstein equation, E equals to mc squared. So if you put a lot of energy into it, it will turn into mass, mc squared. Okay, square of the speed of light. So they do it. So there's a time where they do this a lot, put a lot of energy and then break atom. At that time, every week have a new paper coming out. So the particle they found, they call it a zoo of particles. Almost every paper is about new particles they found. A zoo of particles at that time. So for now, the best theory to describe all these elementary particles is called the standard model. Okay, yeah, standard model. Even though they already reached standard model, okay, but they are still predicted atom to be found. Okay, for example, the graviton. Okay, so who described the gravity? Okay, because why? Because in this world we have four fundamental forces. It's like weak force, strong force. Weak force is like force between atoms. Strong force is like force between nucleus. And then electromagnetic force is what you experience every day. Okay, when you touch an object, it's also electromagnetic force. When you see stuff, it's also electromagnetic. Okay, and then the last one is gravity. So the first three are united under this standard model. Okay, so they have particle to describe strong force, weak force, electromagnetic force. But how about gravity? Okay, so if they can found this graviton, then maybe they can unite the whole theory. Maybe the whole world is just described by one equation. Okay, so they want to find more. So for example, what they do, so there's a society, not society, association called Seng. Okay, I think it's in Geneva, 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 I think. Yeah, and they built this large hadron collider. So they built a large collider. It's like a tunnel, a circular tunnel in Geneva underground because it's very large. And then they use it up a lot of energy. And the first time they, so what they do, they collide two high energy particle beams. Okay, travel at the speed of light. So maybe they took two proton beams and then collide them together. So the first time they collide, the they experience what do you call that? The electricity trips. You know what I mean? It's like 停电 because the energy is too strong. They didn't predict it and then they somehow cannot control it. So they rest about maybe 1 year to repair it and then do it again. And then what they found is the Higgs boson that time. You know Higgs boson? There's a very famous news. Yeah, it's a God's particle, 三 D粒子. When was you last time when the news come up? High school or primary school? Just 2019? Not this recent, right? I think early, right? 2019, 2013? About that, I think is correct. Yeah. Yeah. So so that collision produce more particles is what they do to found the zoo of particles, hoping to found more fundamental particles. So what kind of particle they are interested? So for example, supersymmetric particles, antimatter. So antimatter means if you have matter, antimatter put together, then become nothing. Antimatter. Dark matter. So dark matter is like it's like exists in the dark of the universe. You cannot see it, but somehow there's something there by the calculation they predict. Okay, dark matter. And and perhaps graviton. Okay, so why they are looking for this? Because there are discrepancy between experimental result and theoretical prediction. But this theoretical prediction is typically coming from string theory. Okay, so hopefully string theory can solve all these mystery. But why string theory now is like out of fashion? Because they can't really do any experiment on string. Okay, but 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 this really linked to my research. Okay, so what we did is we have some algebra, and then we try to draw some calculus, which we call string calculus. So we're trying to calculate stuff using string. So and so hopefully these if the maths can be done, then we can do stuff in string. Okay. Okay. You see, the advancement of mathematics, I think the nearest, most fundamental advancement is like calculus. And then you study calculus up to this day. And calculus is invented during Newton's time. So what's the next fundamental uh, improvement? So what's the next fundamental things that people have to learn since high school or primary school? Maybe in future, calculus have to study during primary school, right? Wow, so scary. That would be your son, your children. Can you imagine? Your grandson. Uh, maybe. Okay. Okay then. Okay. Okay. Uh, okay, the last question. Okay, this last question here actually is a hard question. So this question, what happened? Uh, so this question is coming from previous semester assignment question actually. So they only got about 2 hours to do it. Maybe less than 2 hours because they have to do other questions. But you got 2 weeks to do it. Okay. Yeah, that question is supposed to be hard. And then you can see that it takes out almost half of the assignment. Mm, I think I don't have nothing much to comment on this question. So this question's about power series, and then see where the power series converge. You need to use ratio test or other tests. Okay, but if you want to find interval of convergence, radius of convergence, then you need ratio test. But some of you didn't check the endpoint. Okay, you didn't check where the ratio test is inconclusive. Okay, you just do ratio test. Okay, this shows what? This shows you don't do tutorial question. So please do tutorial question. You need to practice. Okay, not just listen and then do. Okay, please do tutorial question. Okay. Yeah. So 2, 3, 4. I think for question 2, what you do is you differentiate term by term, right? Differentiate term by term. And then question 3, what do you do on question 3? Okay, so B actually, okay. So question 3 is about term by term differentiation, but question B is about comparing the two series. So you can just compare them by just factorize the terms, okay? Or I think quite a lot of you just use ratio test again. Yeah, either way is fine. And then question 4, you need to use some clever integrate substitution. I think most of you work it out. I think there's a group of you discussing, right? I see a lot of like taught by Larry. Taught by Larry. Kind of interesting. Why you guys write taught by Larry? I mean, usually we write collaboration. So when you write taught by Larry, what does it mean? Meaning you know nothing and then Larry bring you out of scratch. Is it? You just listen to what Larry said. Is it true?
Yeah, I do from and then thing I try out in time, I also don't know how to do. So I asked for its ideas. So he told me at the first one he do like what, and then I look for myself is going to do that.
Okay. So you say idea from Larry or you say taught by Larry? Yeah, right. So no, usually people will write like this, but some of you say taught by Larry. So what does it mean? So you mean I taught you from scratch. You don't know everything. Ah. I mean, the word you use, right, reflects some attitude. Okay. Maybe because I was studying in Australia, they won't think like that. Because maybe Australians have a lot of opinion. So they will like, how to say, whenever they discuss, they won't 100% listen to you. They will have their own opinion. They will have their own say. Okay, so they won't say I talk by you. Oh no, I don't accept your view. So we discuss, we collaborate. Okay. Maybe I influence you, you influence me. It's not 100% you influence me. Okay, but I observe that Asian sometimes they are how to say, they are more readily to accept people. Not quite. I mean, how to say, I'm not sure how. I mean, I also grew up with this culture, right? Maybe I only have some mind change after I studied in Australia. I was, I, since when I young, I also like, I don't know how to do. Of course, I asked my friend, maybe my friend said, I think, okay, then I accept. So there's a problem with this. I only realized when I do PhD. I only realized when I do PhD. If your friend says something you think is correct, but you don't know why it's correct, but you say, okay, I accept it. There's something wrong here. What's wrong? Most probably, you cannot explain this again to the other person. Because you don't know why it's true. You don't exactly know why it's true. You just pretend to convince yourself. Now, 就是你以为是对的东西，你不知道为什么它对。所以我们现在要 train 这个 degree 可以 train 你的，就是把所有东西搞清楚。这是在数学学科才做得到的事情，其他学科做不到，做不到这么清楚。这个是你要在这个 degree 得到的，把所有东西说清楚，因为我们可以说清楚。So this is the purpose of mathematics. OK，不是说你学会了算这个，我学会了算这个，我出去做工，我准备要算这些，不是。你在算的当中，你把东西全部写清楚。So that's why I ask you, you need to explain every step what you do. Why this equation true? 哎，为什么你可以写等于？为什么这一步可以去到下一步？每一步都要写出来。OK OK， 所以 it's not 不是我随便要求咯，这是我们要达到的准确度。OK precision accuracy. OK yeah. Only Max can give you this kind of accuracy. Okay. Yeah, I think some interesting solution I want to share to you. So, for example, let's see this person here. So, about the cutting half question. This concept can apply in reality, but it is not necessarily true for all physical world objects. For some objects, based on human research, we can say that there exists as the smallest unit which we could not divide it anymore. For example, quantum mechanics told us that energy transfer is discrete. When we transfer energy to an object, the smallest energy unit increasing in the object is by some discrete value. Other than that, humans believe that matter is composed of some fundamental particle which cannot divide anymore. However, we did not have any evidence to prove it yet. That's right. Okay, that's right. In fact, this is how the atom came from. So who's taught about atom model? I think it's called Dalton. Did you learn in your chemistry or not? I think it's Dalton. Okay. And then somehow I don't know, it's J.J. Thomson or who found electron. Either electron or proton get found first, one of them. And then they found something smaller in atom. And then somehow stop here again. And then only go into subatomic particle like quarks, lepton, and so on. Can we go even further or not? Can we go further and further on? Okay, so this is what science need to do. Okay, so there are also some phenomena that could be divided into infinite pieces continuously, such as spectrum of light. Who wrote this? Okay, To Hang Wei. So you read from your own reading. Did you get this from your own reading or? Okay. So where did you do your physics degree? Oh, Utah. So you already finished the whole degree before you come here? Oh, okay. So how old are you now? Okay. How old are you now? 26. Okay. Close to me. Closer to me. I'm 29. Okay. Yeah, I think quite mature from your argument here. Because you try to link to continuous. Yeah. Okay, this guy, you see, although this person didn't write very clear, he just give this geometry series. And we know that this sentence is true. We also can know the objects can be divided further. Thus, the wooden stick can never be cut completely. Okay, I think I remember this one. Is it from Seng? I remember your handwriting. Your handwriting only got 10 lines in your one pages. But it's okay, better. I can read. Too small, I cannot read. Okay. So how you get this idea? Huh? Say what? What did I say? OBG. What did I wrote? Yes. You still remember what I wrote? I can't remember what I wrote. What did I wrote? What did I write? I can't remember. For example. Huh? Oh, can recall what is that? I wrote this one, this one. I mean this one, eh? This one. This one. Where you get this? You sure? How you so sure? Your life experience. Okay, yours. I mean, your argument, right, typically is coming from your life experience. Okay, so coming from what you experience, what you see, what you touch, what you hear, what you eat, what you taste, yeah, what you smell. Okay. Yeah, maybe you can share sometimes. Why you change my question to wooden stick? I put ruler. Oh, how come you got wooden stick one so pro one? Or you read the Chinese one? Why you suddenly change my ruler to wooden stick? Yeah, yes. Okay. Yeah, that's what I thought. I think you translate from Chinese. I should put stick actually. Yeah. Okay. How about this guy? Uh, we encounter limits due to the discrete nature of matters and space. At some point, when you keep dividing a physical object, you will reach a fundamental limit, the scale of individual atoms and molecules. You can't continue to divide a physical ruler indefinitely. It will eventually reach a limit where it cannot be divided any further. This is a fundamental concept in physics known as the Planck length, which is believed to be the smallest meaningful length in the universe. Even before reaching the Planck length, practical limitation come into play. Who wrote this? This. Whose writing is this? Song Yi. Yeah, quite good. So how you get this argument? Also from Google. Do you believe? You believe? Oh, you believe? Okay. Uh, why don't use ChatGPT? Why don't use ChatGPT? Uh, oh, you don't believe? Don't. Okay, so you don't believe ChatGPT, but you believe in Google. Okay. Okay, I believe, but your son must use ChatGPT one. Okay. Yeah, okay, good. So any question about your assignment or not? Assignment solution. Do you have question? And then if you have problem, you should come after me. Okay, when we take a break. And how long you spend doing your assignment? Okay. I, yeah, I can understand for your solution. Why? Who feels stuff written down and then not right. Yeah, please put some part into doing it. Okay. Okay. Yeah. Uh, Yeah, so any question or not? No. Clear, everything clear. Know how to do. If the question come out again, know how to do. Don't know. Ying surprisingly did quite well. Top by Larry. Hey, she got a lot of reference, you know. Every question, he got reference. Top by Rally, top by Zhongyi Rally, and then someone else. And then she got one. She got one question done by herself, is it? Yeah. Yeah, as long as you don't copy, you can learn from each other. Okay. Okay. Another thing I haven't talked about is the mean. The mean is about 24.7, and I think it's quite low. I hope you can improve more. And the mean is quite low, 34. Yeah. And then some of you are in dangerous zone. If you are in about 22, 20, 22 and below, it's kind of dangerous. Dangerous means you are at the bridge of failing this course if you hit this performance. Okay. Yeah. So please at least do tutorial question. Do tutorial question. And then to do good in this class, you need to ask some concept question. To survive, you can do tutorial question. But to do good, you need to deal more with concept. Okay, yeah. Okay, let's take a break until 4:05 will start again. 什么？什么？哦，会家送过来没？家送过来 ，delivery。Is that just nearby? 哦，你是不是 summation 不进去啊？不是有 summation sign？看一下这个题目。因为我是，有 summation 了吗？怎么你 summation 不见的？诶 ，Yeah，因为我从哪里找出来这个公式？诶，对啊，你全部 summation 其实都不见的。诶，Yeah，因为我这公式从哪里来？这样我从上面一开始就没有掉了。像我看一下，有啊，有。因为我是这 part 才没有掉啊。有啊。Yeah，好像我是这，好像我这 part 没有，因为我是梦中的那错。因为我是找回上面然后写，然后问为什么我去掉了。Yeah。OK。啊？什么意思啊？什么意思？怎么可能？怎么可能？这天不够用哦，还提早交不完了哦。老师还要时间补习，还要时间找，对，他时间够。还要找什么？他时间找不定。这样子够。啊，不会可以做。6本。啊，他不是简单的。就是下面就是谁？你那
下来我要把这不给死了，哎，还问你们这个维他维，也是一个老的玩目标，是这样我们我这个持续到这边讲，4年5年，我要找这个这是 K， 这是 K， 你要接受，不是 K， 那个 K 是为了找这个 K， 那个一加那个是为了找那个是为了对，我会比较好的找这个 K， 然后。
你看，你看，
跟 B 嘛，
你看，所以你看，你讲的 exist这个东西吗？我这个东西叫 M， OK， 所以我的 M 是你的 K 啊，所以我现在要找这个是谁 ？OK， 这个东西要符合这个条件，所以我现在找的这个 M actually 是这个大 M 除 B， 所以我这个 M 呢其实是 depend on 这个 M 这个大 M， 对吗？这个小 M depend on 这个大 M， 对吗？
什么意思？还是不明白？对的，这个
OK， 我觉得你不是明白
这
这个东西，我不觉得你不明白这个 definition， 知道这个 definition 是什么？
就是好像有一条线哦，有一条线，然后我那个，然后我那个下面就那边是我那个结棍，那个结，我越来越接近这个，
不是这个，这是 not bounded above。not bounded above 意思说要 for 每一个 M， 每一个数字，每一个数字我要找 AN 大过它。
Yes，
每一个数字我都有一个 AN 会大过这个数字，这样我才会 unbounded 嘛。因为我越来越高的时候都有 AN 大过它这个 N， 所以是说给我一个 M， 我要找这个小 M， 我要怎样找哎？我就用这个找，我的小 M 其实这个大 M 除掉 B。
小 M 为什么是大 N 除掉 B？
啊，为什么呢？你给我一个 M， 我拿这个 M 除掉这个 B， 然后这个 B 是什么呢？这个 B 就是 A 减1。A 减1过后就是我的 B
不得了
啊！
什么？
我说给你看，因为如果假设这个 B 是 A 减1的话 ，A to the power n 就等于1加 B to the n。1加 B to the n 是如果你乘开来的话，就是
很长
一个 binomial 的东西啦。第一个 term 肯定是1嘛，因为1乘1乘1乘1。如果你开掉 B 的话，你会有一个，然后加后面一整串，我也不喜欢，也不想理它是什么。我只要 make sure 这个 term 大过 M 就好了，因为只要这个 term 大过 M， 后面的肯定多出来的 positive 东西，然后这里又有一个1啊，所以你至少都有1加 M 在，1加 M 是不是大于 M？Yes， 像这个就是我要的东西哦，所以我只要设这个 NB 大于等于 M 就好，大于等于 M， 对，大于等于 M 就好 ，which means N 大于等于 M over B。N 是我要找这个 N such that 它大于，
对，它就是这个小 M。
M over B 是这个小 M。
哪里来的 definition？
什么叫哪？
这个我没有看过。
这个不是 definition， 这是我选出来的。因为我要这个 true 嘛，所以我选出来的。我要这个 equation true， 然后我就选出来。我要这个 equation true， 我要这个 inequality true， 所以我就选这个出来了，是吗？你看，我要 prove that 这个是 true 的嘛 ？OK， 所以1加 NB 等于或者大于等于1加 M over B 乘 B，which is 1加 M，which is 大于 M。所以我才选这个。 Yeah.
那 project 哦，是，就如果那 project 的意思是我随便就是我要找一个来，如果我你讲，我现在做一整个这个东西，还是我只是选其中一个敌人来讲，
选一个 theorem 来 prove 就好。
像那个加必定理那个这样子啊，就我选这个敌人来讲，然后我就直接解释这样子吧。
对，要 prove 啊。可是这个有人选掉啊，
会选跟别人一样吗？
最好不要啦，也要有 variety 啊，很难讲，都很容易，可以吗？都很容易，你再选选看，你再选选看，我们学的或者我们用的，但是没有 prove 过，可以后面的也可以，后面也可以。
So this one, right?
Yeah.
At this part, I already show that if the I show it like this one is a sequence multiplication of the many sequence.
Okay, how about we start first and then the next rest you come. Okay. Hello, testing. Okay. Maybe we start first and then if you have any question on assignment, maybe later we will discuss the second rest. And if you want to talk about your project, also can, if you have decided on any topics yet. Okay. Yeah. About the project, right? Actually, there's one open question or conjecture I put inside your Moodle. It's done by a previous batch students. He managed to solve one of the case and he left one as a problem. If you want to solve it, also fine. Okay, as a project. So let me dig up the version first. Okay, so if you go to your Moodle, right? Okay, on this file, okay, the pure file, and then you look for a guy called Li Kai, this person. Okay, so there's a open problem inside there. You can try and see if you can solve it or not. Okay, yeah. So if you open it in, and then he solved one of the easier case, and then see if you can solve conjecture 2. See if you can find counterexample or you solve it. Okay, for this question, right? If you have, if you can solve this question, maybe you can solve it in 2 or 3 a team of people. I will accept if you can do it. You get what I mean? Only if you can either provide a counterexample or you prove it. Okay, you get what I mean? Yeah. Then you guys can write it together for this one. Okay. Either you prove it right or prove it wrong. Cannot prove half one. Okay, cannot do half for this question. If you want to solve it. Okay. Yeah. Conjecture 2. This is something about Swiss theorem. And he tried to relax the, what's it? I think relax the condition on squeeze theorem, but impose condition on series. And then try and deduce something on series. Yeah. You can try and read about it. You also can discuss with me if you like. Yeah. You can discuss more about this question. And then see if you can tackle it or not. Either you produce a counterexample or you prove it. he actually included a false proof here. So actually, in real practice, right, if it is false proof, then we won't include the false proof. So why the false proof is included here? So I want to show you what he did wrong. And what he did wrong in the proof. And then see if you can adjust the proof or not to show that conjecture 2 is correct. Or actually, that's the key to find the counterexample. Okay. Yeah. Yeah. If you're interested, you can discuss with me and we will see. If not, you can look for something that is done before. You can also come up with your own problem and then try and solve it. Okay. 自己想问题，自己解决。Does it sound wrong or not? Yeah. Yeah. Find your own problem and solve it. Okay. Okay. About this part here. So remember last time we solved a power series of EX using OD method, and this is the blackboard notes I put on. There's something wrong here. Can anyone see why is it wrong? I wrote something wrong in the blackboard, but it's correct in the lecture notes. So what's wrong here? Left side not equal to right side. Which one? First line. No, first line. Sorry, I mean, what's wrong about it? Why is this not true?
It is one by ESX, right? Taking SX as an independent variable and then integrate it, I think the result will be SX.
I mean, this one is just a separable variable. I just move the x out and then integrate both sides. Yeah. Yeah. This one is integral over the function 1 and then times dxx. Yeah. This is the usual separable of variable. What's wrong is here. You cannot simply move your function up from your integral. You cannot divide your integral by a function. Okay. Yeah. So how to solve this? I still want this line on up. This line is what I want. I still want this line, so what should I do? I still want the second line instead. What should I do? Yeah, so you work from the dxx dx. So you divide by x-axis and then you integrate both sides. This is what written in the lecture notes. But when I wrote in the board, I wrote this first and then I realized I want this. So I just wrote it down. Okay. Yeah. So we should divide x first and then move dx to the other side and then we'll get this line. So this middle line just don't want. We don't want this first line in mistake. Okay. Okay. So you divide properly first and then you integrate. Okay. Everyone clear? Yeah, this is on the blackboard notes. Lecture notes is okay. Yeah, so when you read lecture notes, right, if you found problem, you should come back to me. Okay, tell us. Okay. Did you guys read or not the lecture notes? Huh? Sorry? Haven't one? Oh, I haven't read until here. Okay, okay. Yeah. If you find any problem, just let me know. So when you read my lecture notes, right, you can compare with the textbook and then see what's the difference, what things I add on, or what things I haven't explained in the textbook that you want to know, you also can ask me. And then maybe we can add it in, add it in, add it in, add it in. Okay? Okay. Yeah. I'm very open one. I'm very open one. Okay, so whatever you want to learn, and then we can learn together. Okay? Because this is not like how to say, this is not like high school or primary school, right? Although we have a main content that we need to learn, okay? But if the whole class is interested in something else, then maybe we can probe into that thing. Yeah, together. Okay. So it's kind of flexible. Okay. So lecture is kind of flexible. Okay, so I think we should continue with Fourier series. Let me see where we stopped last time. Okay, so let's continue with Fourier series. So let's recall what is a Fourier series. Okay, so to do Fourier series, right? What Fourier series apply on? Okay. So let's recall. So what's the Fourier series? Fourier series of f. Okay. What kind of f you are interested in? So these f are periodic f. Okay, so this f is a periodic f. So meaning what? So just now I say mathematics is precise one. Okay. When we say periodic f, what do we mean? There's a mathematic description for it. So what does a periodic function do? It repeats the pattern. So how do you describe this? So how do you repeat a pattern? So you repeat a pattern with a period. Okay, with a period. So this means f have to satisfy some equation such that, for example, fx plus k equals to fx for all x. Okay, and there's this sum k. Okay, so this is the definition of period. So it repeats. Okay, k is the period. After a distant k, it repeats again. Time fx again. Okay, so a Fourier series of f is defined to be what? So the notation we give to Fourier series is capital F with subscript f. Subscripts are small f. So what's the definition? So the definition is in terms of linear combination of cosine and sine wave, because these are the natural source to find periodic function, and then they form basis because they are linearly independent. Okay? And then we look at the span, and then similar to power series, we put coefficient in front of cosine and sine wave. Okay, for example, we call this a0 for the constant terms, and then the coefficient of cos we call an, and then coefficient of sine we call it bn. Okay. So anything wrong with this expression here? Remember last time what I warned you? I have to define the coefficient because on the left I got a f, on the right there's no f. So what's the f doing in the equation? So both sides have to have something involving f. Okay, so where does f involve? F are involved in defining the coefficient. Okay, so how to find this coefficient? You need to do some integral. Okay, some weird integral. For example, a0 is 1 over L, integrate from minus L to L, fx dx. And then an is 1 over L, integrate from minus L to L, fx times cos n pi x over L dx. And then bn is equals to 1 over L from minus L to L, fx times sine n pi x over L. 6. Okay. So so why we do this integral here? Okay. So why we do this integral here? This is what you have to prove in your assignment. Why the integral look like this? Yeah, why the integral look like this? This is what the question 2 in your assignment asking for. Okay, so you need to use the special cases. So the product of cos with different frequency integrate to 0. You need to use that. Okay, so you will see that some terms disappear, some survive. And then what's the survival terms? And you will see that the survival terms is exactly this coefficient here. Okay. Believe my word and then try it out. Okay. Yeah, take my word. Yeah, and go and try. Okay. So this is a definition. This is a definition for example, for your information. This is a definition. So I give you a periodic F. You do this integral here, find this for a series. Okay, this is a definition. So remember, what's the picture you need to keep in mind? What's the calculation we did last time? We have some periodic function. For example, this, right? Okay. So what does Fourier series do to this function? You use sine or cosine wave to approximate this function. Okay. So you have some graph like this. Wait this. Like this. Okay. So if you add more and more cosine and sine wave, this wave here will become more frequent, okay, or smaller, and then closely approximating the straight line. Okay. And what happened at the discontinuity point? Last time we discussed. What happened at the discontinuity point? What does the convergence Fourier series tells you? Fourier series. How do you find the point here at this discontinuity? Limit of what? Limit of what? Okay, let's say this point is S0. Okay, let's call it S0. So limit of x go to where? S0. Okay. From the left of who? Whose limit you are taking about? Huh? Whose limit you are taking about? So let's say our periodic function is f. Periodic f. So whose limit you are talking about here? F. Okay. So you're taking limit from the left, okay, and from the right. And then divide by 2. And divide by 2. Okay. So how you remember this formula here? This formula not only makes sense to the discontinuity point, it also makes sense at the continuity point. Okay. So if it is continuous at this point, for example, this is a constant function. So left and right, the limit is the same. So if you add them up, you double the value. Okay, so you need to divide by 2 to go back to the same value. Okay, so I go to the average of the limit coming from the left and right. Yeah, so that cut nicely at the middle, at the discontinuity. Okay, so this is the convergence theorem. Do you guys want to try example or you want to do it yourself? And try example again. Try what example? Want to try or don't want to try? If don't want, then we go to new stuff. One. Okay, so okay, let's do a example then. Yeah, let's do example together. So yeah, let's look at this function here. So this function is fx equals to x squared. Okay, but I define it only from minus pi to pi. So how do I get a periodic function out of here? Any idea? So what's this function? So let's plot it. This is the x square function. So x square looks like this. From minus pi to pi. Okay, so in particular, the y value is just pi squared. Okay. So this is not periodic. Okay, let's say we want to find the Fourier series of this function. So before doing that, what can we do? We can extend this function. Okay. So how to extend this function? Extend into a periodic function. What can we do? Yeah. Or what's the period of this function? Yeah, 2 pi. Okay. So what you do is you impose x plus f of x plus 2 pi is equal to fx. Okay. So after 2 pi should be the same as before adding 2 pi. So you extend the function. Okay. So for example, you see, at minus pi you have pi over 2. Okay. At pi you have pi over 2 again. Right. So minus pi plus 2 pi is pi. So you get the same. And then you repeat. You repeat the 2 pi interval. So what do you get? Okay, so after extension, what you get is something like this. So after 2 pi, you get the same shape. And before it, you also get the same shape. And then what's the lowest point here? So on the right, you should get 2 pi. On the left, you should get minus 2 pi. Okay, then you can keep extending. So in particular, this is what kind of function? What kind of function is this? Odd or even? Yes. Okay, so from here, you should always observe that this is actually an even function. Right, fx equals to minus fx. Okay, so you already know this is an even function. So before calculating Fourier series, you should expect what? Yeah, there's no more sign component inside this Fourier series. Okay, let's see whether this is true or not. Okay, let's see whether this is true. Okay, so to compute the Fourier series, you just need to compute the coefficient. So A0, AN, and BN. Okay, so just now says that the coefficient of sine must disappear. So you should somehow observe Bn should be 0. Okay, so later we'll compute y is 0. So for A0, what do you do? 1 over L, integral from minus L to L of fx dx. Okay, so our L in this case is pi. Okay, 1 over pi of integrating from minus pi to pi of x1 dx. Okay, What's the integral here? X cube over 3 or minus pi to 1, which is equals to pi cube minus pi cube, 2 pi cube over 3, 2 pi square over 3. Okay, everyone okay with calculation? Do I need to write more? Check. If you think that something wrong, just let me know, then we can check. Okay, how about AN? Okay, AN 1 over L cos minus L to L of x times cos n pi x over L. Yes. Okay. Okay. So this integral, I think, is a bit troublesome. So let's write down what we need to compute first. So 1 over pi from minus pi to pi, and then fx is just x squared, and then cos n pi x over pi. And pi cancel. Okay, so you're left with nx dx. Okay, how to compute this integral here? Put into over and over. How to compute this integral? Integration by part. Okay, I think you just can use integration by part. Integration by part. Do you want to try it out first? Integration by part. I'll let you try first. I think there's no point for me to read out the integration by part step. You try? You try integrate now. Yeah. And then we check the answer together. Yeah. Quickly integrate by part this integral, and then see we get the same answer. Okay, later I want to get answer from Hang Wei. Got answer or not? What's the answer? What's the answer? Huh? What do you get? Hmm? What do you get? No, I mean, I'm just asking you to integrate this. Can you integrate this? Okay, try first. Who got it already? Shen got it already? Huh? Never mind, just try. What do you get? 4n squared cos n pi. Cos n pi? 4 over n squared? 4 times n squared? 4 times m squared? Times cos n pi. Okay. How about the others? Larry got already or not? Still computing. Sing it? Okay. How about Han Wei in front? Have you got it? What do you get? Simplify? Yeah, a bit too long already, I think. Huh? Is that all? It's s squared over n times sine n squared, sine nx plus 2x then x. It shouldn't be x, right? It's evaluated already. No more x here. How about the table with yen rule? You guys manage to get anything? No. Can do by part or no? Can do. Haven't finished yet? Okay. Zhongyi, haven't finished. Oh, Seng it out. Say, you haven't finished. Then you laugh people. Who's that? About others, eh? Kuan Ye. Got it? Huh? Not yet. Chen Jack. Divide n squared. Divide n squared. Okay, how about cos n pi? Where's cos n pi actually? 1 on root 1? 1 on -1, yes, correct. Okay, so depend on n. Okay, how does it depend on n? It's exactly what? Yeah, -1 to the n of 4 over n squared.
Okay.
Okay. Yeah, so if you don't know what to do with by part, this is a choice you need to make. Okay, I have the choice already. Does everyone know the by part formula or not? All right. You know how to remember by part formula or not? How to remember by part formula? Don't know. Where does the by part formula come from? Yeah, integration by part. What do you call that? I don't know what's the Chinese called. I don't know what it's called in Chinese. So how you remember by part formula? It's actually coming from product rule. Okay, so product rule is what? Differentiate uv equals to u prime v plus v prime u. Okay, and then you integrate across everything. Okay, and then what? And then on the left hand side, you get uv equals to integrate uv prime plus v prime u. Okay, so what is the thing you are interested in? Okay, you are interested in one of these. Okay, so set one of them as your question. So maybe I set integrate u prime v equals to uv minus integrate v prime. Okay, so this is the integration. Okay. Yeah. So if you can't remember what's integration by part, you can work out from the product rule. Okay, and then how to pick UV? Here is my choice. Okay, see if your choice match up with my choice. I think otherwise you will keep looping. You can't finish your by part. If you pick a wrong choice, you will not finish your by part. Okay. Okay or not? Okay. You can see that V prime is decreasing. Okay, like differentiating. And then U is like increasing, you are integrating. Okay. So if you choose to integrate polynomial, then the polynomial will grow. Okay, so you need to differentiate your polynomial. Yeah. Okay. Okay. Yeah. What do you get? Cos and pi. So you get 2 pi. So you get 2 pi. I think it's 4. I think 4 is correct. 4 is correct. Log also get 2 pi. No, shouldn't be. I think pi got cancelled. You have a constant 4 over n pi outside, and then the function will give you negative pi. So pi and pi will cancel. You should have a L. Your L will have a pi. There's a contribution from this L here, this pi, and then you will get a pi inside here. It's going to get cancelled. Yeah. Yeah. Yes. So the answer by Chen-Jack is correct. Alternating 4 over n squared. Yeah, that's right. Okay. Okay. If you cannot compute, a bit dangerous. Okay. Please sit down and then write it up. Okay. Yeah. Okay. Maybe we let's take a break. So early. An example finish on the take break already. Okay. Yeah. How about Bn? Bn. So one argument you can give is since this function is odd, so one argument you can show is can give is since f is even, okay, Bn have to be 0. Okay. Or you can just go and compute the integral of Bn. Okay. Yeah. You can use this argument. If you know that it's even or odd, then straight away deduce the coefficient is 0. Okay. Either cos 1 is 0, an is 0, or Bn is 0. Okay. Yeah, you can just deduce. Or If you go and compute, maybe it will take some time. But you sure, of course, at home, you can try and do it. See why they cancel. Okay, see why the odd part disappear. Okay, seeing we spend time on AN, then we don't spend on BN. Okay, so altogether, what is my fx? So what is my ff? So my Fourier series is pi cube pi square over 3 plus the alternating 4 over n square times cos n x coming from 1 to infinity. Okay? Yeah. So you put the coefficient back. Yeah. Okay. Okay, good. Next part for substitution, should we do? Should we skip? Can we skip? Substitution question. Can we skip? Ah, no. Okay. Yeah, let's do. So let's prove. Okay, we want to prove that 1 plus 1 over 2 square plus 1 over 3 square plus 1 over 4 square equals 2 pi square over 6. And then if you consider the alternating version, you will get pi square over 12. Okay. Kind of interesting, you see. If you only alternate the sign, okay, the value changed by half. Okay, how to prove this? Okay, how to prove this? So what do we have here? Okay, so we need to see the similarity between this Fourier series and this term here. Okay. So you have n squared at the bottom here, right? Okay. We also have n squared in my Fourier series here. Okay. So somehow you need to do some clever substitution on your x to read this series. Because this series is what? Is a function in x. Okay, so you want to make it into some number. So you need to substitute the right x here. Okay, so the question give you hints. Okay, so the question give you some hint. So try x equals to 0 and x equals to pi. Okay, try these two numbers. So let's start at x equals to 0. So when x equals 0, what happened to my Fourier series? So we have to put this here. And so this is my f. So if I substitute my x to be 0, what happened? The hand side and the right hand side, actually we both know. Okay. Right hand side, what happened? You just evaluate. So cos 0 is becoming 1. Okay, so you have this series here. Series of pi squared over 3 plus bunch of alternating 4 over n squared. How about the left hand side or right hand side? Yeah. From your side, from my side, right hand side. So what happened here? Do you know about this? Do you know about every point on my Fourier series or not? What does the convergence of Fourier's theorem? This term converges to where? No? This fx converges to where? Half of what? Half of the limit from the left and right of fx. Okay. So we have to go back to see our small f. Okay, let's see our small f at 0. So what happened here? Okay. So my Fourier series at this point should converge to the average of the limit from the left and right. Okay. So what's the limit of little f from left and right of the at 0? 0. Why is it 0? half time 0 plus 0. Okay, so let me write it. So f of little f at 0 is equals to half time limit of x going to 0, okay, from the left of x plus limit of x going to 0 from the right fx. Okay, so when fx equal to x squared, these two are just 0. Okay, half times 0 plus 0, which is just 0. Okay or not? Okay. So does it match up or not from the observation we have? So when it is continuous, just now I say the Fourier series will converge to the same point, okay, at the continuity. In particular, fx, f0 is just 0. Okay, so my Fourier series also should give me 0. Yeah. Any question? So this is by what? By convergence. Yeah, convergence Fourier theorem. This is by convergence Fourier theorem. Okay. 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 So we know left hand side is 0. Okay. How about the other side? The other side is just pi square over 3 plus sum of n equals to 1 to infinity of minus 1 to the n of 4n squared. Okay. So what's this? So what should we do? What should we do to achieve what we want? Huh? What can we do? Move? Sure. Okay, we can move pi square over 3 to the other side. Okay, how about the rest? What are these numbers? So I leave out a square. So there's a 4 in the numerator here. So what should I do? I just move it across. Okay. So I divide by 4 on both sides. And then I'm left with minus 1 to the n of 1 over n squared. Okay. Are we done yet? Not quite done. Why? Huh? Why is it negative? So what should we do? How to move it? Okay, so we just multiply minus 1 on both sides. Okay, so we increase the alternating minus 1 by n plus 1 over x. Okay, so the first term we start is plus 1. Okay, plus 1 minus 1 over 2 squared plus 1 over 3 squared plus minus 1 over 4 squared and so on. Okay, so this is in particular, this is the second equation here. Pi squared over 2. Okay. Any question on this one? No? Is it straightforward? Kind of straightforward. So there are really only one tools here. What's the tool? Two tools actually. So one tool is a Fourier series. The second tool is the convergence theorem. Okay, these two tools. Okay, then you can get the result. There's nothing tricky here. Okay, I think maybe I left you to try the other one. Left you to try. Or you want to try together? Try x equals to pi. Okay. Maybe we just go through. Okay, quickly go through what happened if I substitute pi. If I substitute pi here, what happened? Cos n pi. So cos n pi is what? Just now we computed. Minus 1 to the power n. So minus 1 to the power n, you have two of them. So it becomes what? minus 1 to the power 2n, which is always positive. This is what you want, right? One of the series is always positive. Okay. How about here? What is ff at pi? Okay, you need to go back to your function f here. Okay, so from the left and from the right, okay, look at the limit, average of the limit at pi. So what's the average of the limit here? Pi square. Why is it pi square? From the right is pi square, from the left is pi square. Pi square plus pi square is 2 pi square. 2 pi square divided by half is pi square. Okay. So it's pi square. So on this side is a pi square. So maybe we should write it down there. So pi square equals to pi square over 3 plus sum of n equals to 1 to infinity of 4 over n squared. Okay. Okay. Okay, what? Then what? Then you just okay, then what do you get? Good. And then divided by 4. Okay, good. Okay, so is this pi square over 6 then? Is this pi square over 6? This is pi square over 6. So pi square over 6 is equal to the sum of 1 over n squared. This is the first line here. Okay. Okay. Try and write down fully in your notes. Okay. Does everyone get the flow or not? Can get the flow? Yeah. Very important is the idea. The idea is very important, okay? Because only idea can follow you. Okay, when you explain to people. But to write it down, you need to sit down and write it. Okay, sit down with your idea, then write it. Okay. Any question on getting this series pi stuff? Okay, can follow. Only do one example for example. Okay, today we need to at least finish the chapter Fourier series before we go back. Okay. Before we finish. Okay. We can have a break now. Okay. So we have a break 5:06. When we come back in the next hour, we must finish Fourier series chapter at least. Okay.
Yep. There's another question for right. You deduct me 1 mark here, right?
Okay.
But I just mentioned already, if this thing is true, the sequence is true, then this also true. I mean,
Okay,
it
let's see.
converse.
Okay. Yeah. I mean, you sure that this is this, and then
And then I straightforward can say
we go. You show that AN is increasing. Have you shown SN is increasing?
SN only, right? I mean, I like split this sequence into many pieces.
Sure.
And then if each piece is smaller than 1, then I multiply together also smaller than 1, right?
That one is true.
So I can show that if the sequence, I mean each piece, so I show the 4 pieces of the sequence. If the sequence is increasing and it is bound, have a upper bound is 1, then I show that at here, and then I show that if it satisfy the condition of this I mean theorem, then is converse.
But you didn't. You only deduce that. You only deduce that if AN. But you haven't really. Okay, so how? Okay, so wait, so you want to deduce SN is convergent, okay? You said this follows from here. Is it?
It's follows from actually.
How to follow it? Here just says that it is bounded, right?
Yeah.
But to use, then how to deduce? You just say bounded sequence. How to deduce something is convergent?
That it is infinity, right?
Here. Oh, sure. Yeah, of course. But I mean, if a sequence is bounded, it might not be convergent. For example, 1 and -1 is bounded, but it's not convergent.
I mean,
so you need more. Yeah, so you need to show Sn is increasing as well. But what you have shown is just showing that An is increasing. Why Sn is increasing or decreasing? You know what I mean?
You say that it is my like.
So you cannot deduce convergence from here. You cannot deduce convergence from here.
But
Yeah.
Let me think.
You get what I mean or not? You just show that here is bounded, so Sn is bounded. Okay, sure. So to use monotone convergence theorem, you need the sequence to be monotone as well.
就是讲它就会
increasing or
到一
decreasing.
个 value， convert 就是讲到就是一边一会变成一个 value 了。我只是说它只是 bounded 到
You need monotone.
Okay, monotone.
Yeah. But what you have done is you show An is monotonely increasing. Unless you can deduce from there Sn is increasing. Okay.
I'll check the question. The quiz theorem. I think
Which theorem?
About the one that they didn't manage to prove. I think so first this assumption is correct, right? Like UN, SN, TN in order.
Let me read the question. Suppose the error is true if both convergent, then what to show? Let me think. So you don't take this condition in?
Yeah. Apparently, I don't think they actually also use that.
You don't use it? You don't need this?
Yeah, I think it's not needed. At least I didn't use it.
Not needed. Okay, let me see first. You don't need that. So what do you do? So since S2 converges, yeah, this conversion. Then this one converge. This converge. No counter example. Take this as N0. Okay, let me check again. Bush in particular. Property. Okay. So step converge. So it converges. See, this guy converge. UN also converge. Then we can add them together. I think it works. With this actually don't need that. Both here. I think okay. I think okay. But I'm not sure this is the initial what he thought. I think at first I think because we know that this is 0 implies that this is 0. But this is 0, this limit is 0 doesn't imply the sum is converted. So I'm not sure which condition is decay more. Okay, but for this statement, I think it's correct. Yeah, you can try and write it down. And then I will try and, okay, you write this down and then you send me. And then I try and talk to this guy again. And then see, is this the what he initially thought? Okay or not?
Alright.
Okay. Okay. Yeah. Okay. Yeah. So yeah, you try and write this improper properly, and then you send me. And then I'll talk to him. And then see if this is what he wants last time. I can't really recall what he wants. Okay. Let me ask him again. Okay. Okay. Thank you. No. That's it. Okay. So Larry so Larry, just now kind of came to solve this question here. So this question here, right, doesn't, how to say, it's come out from one student. Okay, so you can also come up with your problems. So, so let me solve without using the limit. So I will try and get this proof and then try and ask the student again. I guess see is what we really wanted last time. And then, yeah, and then we'll see. Okay. Yeah. So they put conjecture here because he wrote there he cannot produce a counterexample to that statement. Yeah. And then he want to solve this, and then he try and relax some condition, and then until that he get this kind of example here. Yeah. I mean, this is the way we do maths in a proper real world. So we have a problem, we don't know how to solve. Let's see if we can relax the example and then we can solve or not. And then found out that we can, but we still can't quite solve the real example, real question. So and then need to try some more. Okay. Yeah. Okay. Right. Okay, let's continue with Fourier now. Okay, maybe I show you the picture faster than. Show you the picture. Okay, so next we'll talk about this Fourier cosine and Fourier sine series. So what are we doing? So sometimes we have a function. Okay, just now we extend it periodically, but actually we can choose to extend it as an even function or odd function. Okay, so if we extend the function as an even function, it's what we call a Fourier cosine series. If we extend the function as an odd function, then it's what we call the Fourier sine series. Okay, let's look at one example here. So let's look at this function, piecewise function. Okay, from 0 to 1 is x, from 1 to 2 is 2 minus x. So what is it doing? So it's like going uphill from 0 to 1 and then going downhill from 1 to 2. There's a triangle, peaks of triangle. So if I gonna extend it evenly, so what does it mean by evenly? So meaning fx equals to minus x. So meaning across the point x equals 0, there has to be the same f. There has to be a same f. Can you imagine how it happens? So across here, you have to have the same f. Can you imagine what is going on here? So let's say you want to extend this function fx, fx equals to minus f minus x, right? Okay. So across x equals 0, there has to be the same f appearing here. Okay, so can you imagine what kind of picture you need to draw? Okay. So for example, f1 is 1. So what happened to f minus 1? It's also 1. Okay. f1, f2 is 0. F minus 2 has to be 0. Okay. And then similarly, f0 is equal to f0, so it's still f0. Okay. And then what's next? F half is half. So f minus half has to be minus, has to be half as well. Okay. And then f 3 over 2 is half. So f minus 3 over 2 is also half. So you get the same triangle. Okay. So how this? So you just repeat the triangle. So this is the even function. How about odd function? How about odd function? How about odd function? How about odd function? Instead of equal to f minus x, you need to take minus f minus x. What does it do? Flip across the horizontal axis. Okay, fx become minus x. Okay, so you will get, instead of upward triangle, you get downward triangle. And then you repeat this. So you repeat this, so what do you get? Like this, and then like this. So you repeat this. So this is the two extension you will get. So if you extend evenly, you will just get all the triangle upward. And then if you extend oddly, then you will get up, down, and up. Okay. So yeah, so this is graphical. So we need to find the Fourier series. So how do we do the Fourier series extension here? So what we do? Okay, so what do we do? So to find the first series, cosine series, which is even, since it is even, right? Then Bn is just 0. Okay. And then how to find An? Okay, so to find An, you do the same thing. Okay, you just integrate. So let me write down. So your An is equals to 1 over L, integrate from minus L to L of fx times cos n pi x over n dx. Okay, you do this computation here. There's nothing special here. You just need to do the integral. Okay, so for example, in our case here, we still need to compute a0. Okay, so what is a0? So integrate from minus L to L. So let me write down. 1 over L. L in this case is where? Is from 0 to 2, right? From 0 to 2. See? 0 to 2. So, okay. I think we should determine this period first. Where's the period? Where's the period for these two? Sorry? Minus 6 to 6. I think you can pick that as your period, but not necessary. Okay, you can pick the smallest one. For even, right? For even case, I think you can pick minus 2 to 2 or 0 to 2. Yeah. Okay. So you can pick the period like this. So this is your period. Or you can try this as your period. P1, P2. Try if you get the same answer. You're gonna try. Yeah. Try and let me know next time. What do you get if you try a different period? You should see that if you choose this period, right, you should get the same function. Yeah. So do they give the different Fourier series or not? I think shouldn't be, but you can try it out. Okay. How about odd extension? What is the smallest period you can pick? What's the smallest period you can pick? Minus 2 to 2. Okay. You need to repeat the downward triangle and the upward triangle. Okay, so this is the smallest you can pick. Okay. Yeah. Okay. You cannot pick minus 4 to 2. This is a different picture already. Okay. So if you pick minus 4 to 2, you will get something like this, which is not the same. Correct? It's not the same. This. Okay, this is not the same. Or you can pick maybe minus 6 to 2. Yeah. I think it's a good example. You try a different period, see if you get the same thing. My guess is they should get the same. Okay. If not, then we need to argue why they give the same Fourier series. They are the same Fourier series. I think it's exactly the same, but we should try. You should try first. Okay, so in this case here, what I did before, what I did before. So let me check what I did before. Okay, so actually my period here is getting from minus 2 to 2. Okay, yeah. So what is the calculation did in my lecture notes is from minus 2 to 2. Okay, and then I use the fact that it is even. So I just compute half of it. If you want to compute all of them also can, meaning if you want to take 1 over L integrate from minus 2 to 2 also can, you should get the same answer. Because it's even, you can cut it at half. Okay. So if you don't want to cut it in half, you can do half times integration minus 2 to 2. also works. It's the same. Okay. Okay. Yeah, how about AN? Okay, AN is a bit troublesome because you need to multiply fx with your cos. Okay, but usually you need to use by part. Okay, so let's don't spend time doing by part here. So we do by part, and then we will get this long expression here. And once I get this right, you can try and put into the computer. Okay, try and put into a computer of this Fourier series. See you get something look close to this original shape or not. Okay. So once you get your Fourier series, try and put into online computer, graph it for you. See, do you approximate your original f1? Okay. If it doesn't approximate, maybe your calculation is wrong. Okay. Yeah. So your Fourier series should be something like this. And approximating the graph. Okay. Similarly, you did it for your odd series. Okay. So in this case, how to say? In this case, this Bn right is fixed by you because you want either odd or even extension. If it is an even extension, you need to set your Bn to be 0. If it is an odd extension, you need to set your An to be 0. Okay, this is set by you. You cannot compute one. If you compute, you will get answer one. Right? So if you compute Bn, actually Bn works here. Okay? But if you just keep your Bn and throw away your An, this is what we call the Fourier sine series. Okay? If you throw away Bn and then you keep your An, this is the Fourier cos series. Okay? So this is purposely made. Okay, it's not what we did before. Before is we like testing what is our function. Okay, but here is a purposely made one. You want a Fourier sine series, or you want a Fourier cosine series. Okay, so you want odd extension, or you want an even extension. Okay, so this is a purposely done one, not by nature. Okay, yeah. Next, we'll talk about a Fourier transform. We won't go deep into Fourier transform. What you need to know is how to compute. Okay. So a Fourier transform is transforming a function in time into a function in omega. Okay. Now you have no idea, it's okay, because later we will introduce how to do Fourier transform. So in general, what it means is you have a function in times. Okay. And then you want to turn into a function in frequency. So you want to reach what are the frequency lying inside here. So you can see that this is like a linear combination of different weight. And then we read out what kind of frequency you have, how much of this frequency you have after Fourier transform. Okay. Yeah. So this is just concept. I haven't defined yet what is Fourier transform. And the Fourier transform is closely related to complex Fourier series. Okay. So what does it mean by complex Fourier series? So just now what happened? So let me recall again. So what's the definition of Fourier series? So you have some constant. Okay, you have some constant plus linear combination of cosine and sine wave. Linear combination of sine and cosine wave. Okay. So in particular, all these number right are in real actually. Okay, so all these number are in real numbers. Why? You see, what is this A0, Bn? These are just integral of fx with trigo function. Okay, so this, for example, an is fx times n pi x over lambda dx. So you see, so you are taking product of real function and then integrate over real interval. So what you produce is a real number. Okay, so this is an is a real number, cos, sine are real function. Okay, so real number times real function is still a real function. Okay, so this whole thing evaluate to real number. So it's a real function in particular. So that's why you draw them in the same graph. Okay, it's really a function from R to R. Okay, so they are living in the same space. But now in this case here, we define a complex Fourier series, meaning we have real and imaginary part. Okay, real and imaginary part. So how this comes in? Okay, how this comes in? So this comes in by this Euler formula here. Okay, so you to know how to read about this part, you need to know about this Fourier Euler formula. So Euler formula is e to the ix equals to cos x plus I sine x. So this is a generalization of e to the I pi equals to -1. Okay, so this is what discovered by Euler. Then people generalize this formula here. So what happened if I change pi? If I change pi to minus pi, what's the value? Or pi over 2, what's the value? Okay, so people generalize to all angle and deduce this formula here. E to the I pi ix equals to cos x plus I sine x. Okay, so this is a generalization of Euler formula. Actually, this formula has another name. It's not Euler formula. Anyone remember or not? De Moivre or what? Is it? What's the name for this formula? This is a generalization of Euler formula. D something, I think. Huh? De Moivre, huh? De Moivre. So it's a DEMOIVRE. De Moivre. Okay. So this is a generalization of Euler's formula. Okay. Yeah. Okay. So how this came from? Okay. So let's look at the derivation here. So let's take these two formula here. Let's look at these two formula. Okay. So I claim that I can make cosine and sine x out of e to the I sine x and e to the minus ix. You know how to make it up. So how do you express cos x using these two exponential functions? Yeah, try stare at these two equations. So how to build cos x out of these two? How to build cos x? Huh? And then yes, okay. So you add them up, the imaginary part cancel, and then divide by 2. How about sin x? You take the difference and then 2, just 2i. Okay, you need to divide the imaginary. Okay, so this is the so this is how you express trigonal function in terms of exponential. And then you can do some experiment here. Okay, so we can express, in particular, we can express our Fourier series in terms of these exponential function, right? Because we just translate our cosine and sine function into these exponential function. Okay? And then if you collect the terms e to the I x n pi over L and e to the minus I n pi over L, you will get this combination of coefficient here. Okay. Okay. Okay, so what you observe here, there's something to observe here. So you see, there are two terms of exponential. Okay, one is n pi x over L, one is minus n pi x over L. But my n is going from 1 to infinity. So meaning one of them is going from 1 to infinity, the other one is going from minus 1 to minus infinity. So now you are like summing doubly infinite sum. And sum from 1 to infinity and then minus 1 to infinity. Okay. So you sum two ways now. Just now, Fourier series just sum one way from 1 to infinity. But now you are summing two ways. Okay. Okay. So we will redefine this coefficient. Maybe we call it C0, Cn, and C minus n. Okay? We collect all these coefficients. And then where's the formula? So we define this complex Fourier series. So we will define complex Fourier series as this summation here. Okay. So this is summing from 1 to infinity and minus 1 to minus infinity plus 0. Okay. Yeah. And then this coefficient, how do you get this coefficient? You just take fx multiply with the exponential function and then integrate it. Previously, you do it on cos or sine. Now you do it on exponential function. Okay. Yeah. So not that this sign here, not that this sign here is like opposite to each other. So if you want to find coefficient of Cn, a coefficient of e to the I pi nx over L, you need to multiply your f with e to the minus I pi nx over L. Yeah. Yeah. So this is something you need to know. Eventually the e will be gone. What do you mean? Will the e be cancelled? Yeah. So how they cancel? They cancel. So suppose, for example, okay, let's do some experiment, right? So let's say this is my f. Okay, if I express my f like this, how to find my Cn? Okay, so this formula tells you that you need to integrate. You need to integrate this function multiplied by e to the minus I n x over L. Okay. Okay or not? So let me write a little bit more. So Cn, or maybe use another color. So Cn is equals to integrating minus L to L of 1 over 2 pi. Let's say my f is already written in that form, so it's just of infinity, and then Cn of e to the pi n x over L of e to the minus I pi n x over L. And but not that, here a very crucial thing here is multiply with every summation. Okay. Can see or not? Okay, run see. I'm somehow giving hint to assignment 2 by the different form. If you can try and listen carefully and then ask question if you need. Okay, so let's say my f is written in this form. Okay, so why we define Cn in this way? Okay, so let's say my f is in this form. Try and compute what is Cn. Okay, so what happened here? You need to multiply e to the minus I pi n x over L to all of these infinite terms. Correct? Okay, but my claim is only one term survived. Only one term survived here. Okay, okay. To be precise, you see, very messy here actually. Actually, I don't like this. Very messy. Why very messy? Here n is a indexing number. here n is actually a fixed number. So maybe I want to change this. So maybe I change with p. Let's say I want to find CP for 1p. Okay. So my claim here is, although you are multiplying with infinitely many terms, only one term will survive inside it. Which term? I mean, survive under the integral. Which term will survive? C0? No. Not C0. Now, which term will survive? Survive under the integral, I mean. Seng, you know what am I asking? What is survive? Survive you must know, otherwise you will be dead. You'll be dead. What is survive? Okay, which only one term will survive here? Which term? Under the integral. Okay, so my claim is when n equals to p. Okay, what happened when n equals to p? What happened to these two terms? They cancel. Okay, then you left with Cn. What about the other terms? When n is not equal to p, they also have a similar special cases for exponential functions. So if you combine if you take a product of different exponential function of different frequency or period, then the integral is 0. Okay. Yeah, the integral is 0. Similar to the cos. If you take two cos function, integrate the product of two cos function with different frequency, you also get 0. Remember the condition if m not equals to n. Okay, let me rewind for you. So this is the picture you should have in mind. Okay, so if you take the product of two cosine function with different frequency, you should get 0. This is also true for exponential function. Okay, can get it? Okay. Let me write down something. So integrate from minus L to L e to the I m. Do we have pi? Pi x over L times e to the I n pi x over L dx. You should also get 0. Okay. You should have a similar special cases on this exponential function. Okay. Because in the end, what happened if you multiply two exponential functions together? You are getting the cross term coming out from cos x plus I sine x. You are getting the cross product term. Okay, so in the end, it also boils down to these special cases. Yeah. So the only term that survive is when n equals to p, because p minus p there cancel out for these exponential. Yeah. Okay, so the only term survive is CP. Okay, yes. Okay. Yeah, but what is this? This is just 1 over 2L times CP times 2L. Okay, yeah, it's CP. Okay, Any question you want to ask about? Any question? If any part not clear, you also can ask me to clarify. Yeah. Imagine this graphically. Which one? When n is not equal to p. Yeah. How you imagine that? So if you have different m and n, right? So it means you have different frequency. You know. So yeah, so why they cancel out is a good question. So why the integral compute to 0 when they have different frequency? Why they cancel out? Yeah. You can think about it. Yeah, maybe you can try and prove. Try and draw and prove in your project. Then everyone can learn why is it true. You can draw in your project and then compute and then show in the figure why the integral have to be 0 if the frequency is different. Okay. Okay. But for the sake of your assignment, you just need to use a special case. Okay. Okay. Any question? Any question? Okay. Okay. Continue. Continue. Okay. If you have more questions, we always can come back one. Okay. So we define the Fourier series as follows. So and we have this capital F. Okay. Apply on ft. And then we have new variable now called omega. Okay. So where does this omega come from? You need to multiply ft with e to the I omega t. Okay. Integrate from minus infinity to infinity. Okay, the difference between Fourier's transform and Fourier series. So Fourier transform here don't need to start with a periodic f. Any f will work. Okay, no need periodic. But Fourier series, you need to start with a periodic f. Okay, Fourier's transform no need. Any function you give me, I can transform for you. Okay, no need periodic function. Fourier series only work for periodic function. Okay, because you need to write it in cos and sine. But in this case here, no need. Okay. In this case here, Fourier series only. Okay. How about inverse Fourier series? Okay, so inverse Fourier series, what you do, instead of multiply by e to the I omega t, you multiply by e to the I omega t. No need the inverse, no need the minus. And then divide by this 1/2 pi here. Okay. Divide by this constant, 1/2 pi. Dividing this 1/2 pi, there's a reason. Okay. Yeah, there's a reason about that. Let's see, we will get to the reason or not. Maybe we won't. Okay. Next. So why we call it an inverse? Because if you do Fourier transform and then you inverse it, you will get back your function. That's why we put the inverse here. Okay. Okay, next. Let's try find Fourier transform of a function. Okay, so this Fourier transform, you can see that where does this function lies in? Where does this function lies in actually? So E is a complex function. Okay, so this whole terms here will give you a complex function. So you input a real function, it gives you a complex function. So what does it mean by complex function? It is a complex value function. So meaning if you input a real value function, it will give you a complex number. So how to plot complex number? You will plot it on the R2 complex plane. Okay, so let me write down something. So F will make your real value function into a function in real to complex. Okay, so Fourier transform of a real value function is a complex value function. So to plot this Fourier transform, right, you need to go to the complex plane. So what's the complex plane? Complex plane is the equivalent to R2. Okay, so equivalent to R2. So the horizontal is X, vertical is IY. Okay, so you will plot it on here. So where is R? You can think of R as a time. So at time equals 0, where is it? And then time equals to 1, where is it? Okay. So it's like circulating around the complex plane. Okay. There's an animation of this actually. So you can try and look at the video by 3 Blue, 1 Brown. There's a conceptual 3 Blue, 1 Brown. There's a conceptual introduction to Fourier series, Fourier transform using animation. Okay. Yeah. But for the purpose of this class, right, you just need to compute. That's all. Okay. So what you need to know is this formula here. If you want to Fourier transform a function, okay, you multiply by e to the I omega t and then integrate from minus infinity to infinity. Okay, I think you should ask one question here. You are integrating from minus infinity to infinity. This is a large interval. Most probably, this integral won't converge. Okay, so the example we will show you is all easy example. They don't go to that far. They will vanish after some finite interval so that you can compute. Okay, so for example, in this case here, okay, so let's look at this function here. T less than 0 and then t greater or equal to 0 of piecewise function. When it is less than 0, you get 0. When greater or equal to 0, you get e to the minus at. What's this function? This is an exponential function. Okay, so let me try and graph this. So when t is less than 0, it is just 0. Okay. And then when it is t is greater or equal to 0, is e to the minus at. E to the minus at is decreasing. Is decreasing. Okay. So decreasing from, in particular, decreasing from 1. Okay. If increasing, diversion. Okay, but this is increasing. And then increasing fast enough. Okay, decreasing fast enough. So we can try and compute the Fourier transform. Yeah, let's compute the Fourier transform. By the way, there's a notation here. Let me introduce this notation here. If I post out the note, if you see this notation, there's a ht times this function here. What is ht? Ht is called a heaviside function or a unit step function. So meaning you truncate everything less than 0 and then introduce 1 to everything greater or equal to 0. Okay, so this picture here is here. Okay, this is the picture. So this is a unit step function or a heavy side. So it's heavy on one side. or is a step function. Okay. And then if you have this function, what is the function I gave just now? You just scale the number 1. You scale the 1 by e to the minus at. So you scale it down. Okay. Of course, you scale the 0 part, but 0, you scale it, you did nothing. Okay. So it's really just a heavy side function multiplied by some constant. Okay, so this is the notation. This notation won't be helpful for this course, but in future you will meet this unique step function again. Okay, so let's say we want to Fourier transform f1. Okay, so what do we do? So the formula is integrating. So let me write down. So if I draw here, okay, so maybe we just draw here. So let's Fourier transform f1. What's the notation here? So f1 t omega. Okay, new variable from minus infinity to infinity of f1t times e to the I minus I omega t dt. Okay, so this is what you need to do. But this integral here, right? What happened? What happened when we do on this function? Half of them is already disappeared, right? Because when t is less than 0, it is just 0. So this integral here actually start with 0 to infinity. And the expression for f is e to the minus at. Okay. Okay, so we plug this in here. So we do this calculation here. So we Fourier transform f1 is just integrating from 0 to infinity of e minus at times e minus I omega t. Okay. And then we combine the power. So how to integrate exponential? So I think it should be easy. So you just get the exponential back, and then divided by the power. Okay. And then note that this is an improper integral. Okay, what you need to do, you need to integrate from 0 to k and then bring k to infinity. Yeah, you need to do the improper integral. And then what you get out is 1 over a plus I omega. Okay. So is this surprising or not? 1 over a plus I omega. A is a constant, omega is the frequency. Okay. But this is a complex number. What's this complex number? What's this complex number? Actually, you can use what you have learned in power series to compute this guy. So how to compute this guy actually? How to use power series? 1 over a times 1 over 1 plus I omega a. Okay. And then 1 over a times 1 plus I omega a plus I omega a square, and then so on. Minus it? Yeah, minus. Correct. I think you're right. So minus. Because the O positive one is 1 minus, right? But this one is so I think minus start from here, right? Minus on the odd term. Okay. So if you can compute this, then this is the complex number you get. Okay. Yeah. Okay. So similarly, you can Fourier transform the other guy. Okay. You can try it out. And then you will get. So the other guy, what happened here? E over at with t less than 0. So actually, you just reflect this graph here. You reflect this graph. So E over at for less than 0. So it's decreasing when t is negative. And then when t is positive, it is 0. So it's like reflecting. Okay, so F1 and F2 is a reflection on x equals 0. Okay, yeah. So the result of Fourier series is a reflection on here, the denominator. One is a plus I omega, the other is a minus I omega. You can go through the similar computation again, and then you get 1 over a minus I omega. Okay. Yeah. For this Fourier transform Fourier series topic, right? You just need to know how to calculate. That's all. So that's why I don't want to spend too much time here, because if we really want to go deep to this chapter, it's really deep, and you will do this in future. Yeah, it's really hard, this topic. Yeah. So for this course, you just need to take the function, multiply with the right cosine function or sine function or this e function, and then do integration. That's all. And then the integral won't be hard. Yeah. The hardest one is a by part. Yeah, that's all. And make sure you know how to do integration. Okay. Yeah. Okay. So for example, maybe we don't go through the computation. I just quickly go to what will the Fourier transform happen. So let's Fourier transform a function. We call it a pulse function. Okay, why is it pulse function here? So you can see that this is a piecewise function in 3 parts. Okay, piecewise in 3 parts. 0 when it's less than minus a, 0 when it's greater than a. And then in between, what happened? What happened is you put 1. Okay, so it's like ding, like this. Okay, or something like this. And so you are dead, and then come out again, and then you are dead, and then come out again. Okay, pulse function. Okay, and then so if I Fourier transform this, okay, you do the same integral. So you see, your integral is going from negative infinity to infinity. Okay, but what happened? At far infinity and far negative infinity, actually, there's nothing. Okay, what you integrate is really from minus a to a only. Okay, yeah. So if you integrate this, surprisingly, when you integrate this, what happened? There's only real part appearing. There's no imaginary part. There's only real part coming out. Okay, you see, only 2 over omega times sine a omega. Only real part, no imaginary part, no I times something. Okay, so you can plot it on the same, really the same type of graph. Okay, so what happens? So if you Fourier transform this pulse function, what you get is this frequency function. Okay. And then if you do inverse Fourier transform of this Fourier transform function, then you will get back your pulse function. Yeah. So can you see that somehow it's a little bit similar to what we have just now, but it's different. But it's different. Okay. So just now, if I do Fourier series, right? Let's say I repeat periodically. Okay, what I get from Fourier series is graph like this. Okay, but now you are getting this frequency graph. So it's a bit different, these two construction. You get what I say? Okay, so the Fourier series picture is like this. But the Fourier transform picture is like this. Okay, so these two are really different construction. Don't confuse them. Okay, because you get different things. Okay, so let's look at one more example. Let's say we want to Fourier transform this guy, e to the minus at squared. Wow, this guy is a bit crazy. This guy, what is this? Just now we truncate it, but now we don't truncate it anymore. So this is e to the minus at squared, something like this. Okay. So what happened? Oh, actually, if you multiply by e to the I omega t, this integral surprisingly converge. Okay, and then why is it converge? You need to use something from the probability class on this. And I think this is called Gaussian distribution. Is it normal distribution? Normal distribution. Okay. Yeah. So you need to use this to calculate the integral here. And then you get this again. So see here, what do you get? Here, what do you get? Oh, actually, I give you the wrong picture, right? So here is t squared. Here, this one is e to the minus at. So what happened to t squared? Yeah. Where's the t? Yeah, where's the t? Okay, so this t here is the horizontal t. Okay, and then here is the ft. So what happens if you take t squared? Why this one grow up? Why this one grow up? Why this part grow up? If I put e to the at. Okay, we just sub value in, just sub values in. So for example, -1, what happened? Become e to the a. -2, 2a. -100, 100a. Million a. Okay, so it grow out. But what happens if I put t squared? Why go down? Yes. Okay. So what happens is it like imitate what happened on the right hand side here. So it come out here and then go down. Okay, so go down. So like this, and then here go down like that. Okay. So it's like a mirror at the x equals 0. Okay. So this is the right picture if you look at t squared. Just now we look at e to the minus at. Okay, now this one make more sense, right? So this one make more sense. Okay. So it converges fast on both sides. So that the integral from minus infinity to infinity converge. Okay. Yeah. Okay. So converge to this guy. So what's the picture here? So the bottom here is the original function, okay, Gaussian function, and then this is the Fourier transform we make. Okay. So there's a difference in height here. There's a difference in height here. So if you look at the 3 blue, 1 brown, they will mention something about this height. This is the frequency. Yeah, but maybe we don't go into that because won't be tested also. Okay, last two thing is these two. So first is Fourier transform is linear. Okay, so if you Fourier transform on some linear combination, you can do Fourier transform on individual function first, and then multiply by constant, and then take the sum. Okay, so it's linear, and then it is symmetric. Okay, so if you Fourier transform twice a function, okay, so if you Fourier transform a transform function, what you get is you get back your original function, multiply by 2 pi, and then reflect on omega. Yeah, so if you transform twice, okay, so if you do ff twice, ff, so f squared on little ft, what you get is 2 pi on f minus omega. Okay. Yeah. So you get back your function, and then multiply by 2 pi and then swap on the variable. If you are interested, I will put the proof in and then you will see. But I think this identity we won't test you in class. So what I will test you in exam or what is to maybe compute Fourier series, compute Fourier transform. That's all. Okay, for this chapter. Yeah, this not so important. But I will attach the calculation and proof if you like to read. Okay, but for this special chapter, you just need to focus on how to compute Fourier series, how to compute Fourier transform. That's all. Okay. This property not so important for the test. And then this chapter is really hard, and then you will see it in future. Okay, in future advanced course. Okay, and then we have done with Fourier series, and then on Thursday we will start with curves. Yeah, really doing calculus now. Okay. Okay, we'll see you on Thursday.
Yeah. Oh, the system has